A magneto is a component that self-generates the necessary energy for the vehicle's ignition system. CDIs have replaced older magneto systems and have found their way into light vehicle, motorcycle, marine and outdoor power equipment. When rotated by the engine, the magneto is capable of producing a very high voltage. This eliminates the need for a battery as the source of external energy. The working principle of the magneto ignition system is the same as that of the coil ignition system. The primary circuit magnetic flux is collapsed across the secondary circuit and high voltage is induced in the secondary coil windings. The most common type of magneto ignition is the rotating magnet type and is found across all aspects of marine, motorcycle and outdoor power equipment. This type of ignition system uses a crankshaft mounted flywheel, which houses a set of permanent magnets. As the crankshaft rotates, the flux from the permanent magnets will pass over a set of exciter coil windings mounted behind the flywheel. This movement of the magnetic flux induces current flow in the exciter windings. The winding is connected to ground on one side and the ignition coil secondary on the other. A cam-driven contact set completes the circuit back to ground. When the contacts are closed, current from the exciter coil flows to the primary windings, building the magnetic field. As the flywheel magnets pass the exciter, peak voltage is reached in the primary coil. At this point, the contact set opens and the magnetic field in the primary coil collapses across the secondary windings. A capacitor connected in parallel with the contact set speeds up the collapse of the magnetic field by providing a ground path for the exciter current when the contacts open. The collapse of the magnetic field induces current to flow in the secondary circuit. The exciter coil is capable of producing around 150 volts AC, so the output voltage of the secondary winding is stepped up to about 15 kilovolts. Regardless of the type and location of the exciter and ignition coil, the operation will remain the same. Let's look at a simple CDI system for a single cylinder engine. As the flywheel rotates past the exciter coil, the magnetic flux induces an alternating current in the windings. The alternating current is converted to DC via a rectifier assembly in the CDI module. A capacitor or capacitor bank is charged by the exciter coil. This charge is only held in the capacitor for a brief time. The potential across this type of capacitor is about 150 volts. The inductive trigger device mounted in close proximity to the flywheel is influenced by a tag mounted on the rotor. A very small current is induced into this pickup and is sent to the base of a switching transistor. As we can see, the transistor is mounted in series with the primary windings of the ignition coil. When the switching transistor is triggered by the pulse from the pickup coil, the stored energy in the capacitor flows through the transistor and primary coil windings to ground. The voltage flowing through the primary windings induces a much greater voltage through the step-up secondary windings. This voltage flows to ground via the spark plug. The location of the pickup coil determines the timing or trigger point of the spark. These inductive triggers are generally mounted to an adjustable plate, allowing the timing to be altered. One of the advantages of CDI is that they are able to produce high voltage at idle to be on the engine's redline, whereas an inductive type is hindered by shorter saturation times at higher RPMs. This is because capacitor discharge ignition draws its voltage supply directly from the battery. It incorporates a transformer that steps this voltage up close to 500 volts in many systems. A capacitor or capacitors in the ignition module store this high voltage and releases it to the ignition coil or coils when triggered. An integrated circuit is used to limit the voltage produced by the transformer and to control maximum engine RPMs. Due to the rapid charge, discharge and switching of the various electronic components that make up a CDI system, it must be housed within a very large heatsink. The downside of CDI is that the spark produced, although very strong, has a very short duration. This isn't a problem at higher RPMs, but could be at lower. However, due to the increased voltage and nearly instant recovery of CDI, the spark plugs may be fired multiple times on the same cycle. This multi-spark function can be built into the integrated circuit within the CDI module. At idle speed, there may be 5 or 6 individual sparks. As the engine speed increases, the number of sparks decrease. Generally, most CDI systems produce multiple sparks up to about 3000 RPMs. Due to the very high primary voltage produced by CDI, ignition coils can be engineered with outputs of around 70,000 volts. Although this is somewhat overkill for a passenger vehicle or motorcycle, it has been adopted by the performance markets. These are best suited for engines that require incredible spark power to ignite exotic fuel combinations under high compression circumstances. You may not see a Magneto or CDI system on every vehicle that enters the workshop. But when you do, a solid understanding of this type of ignition will make the job a whole lot simpler. Thanks for watching.